schools have been closed, so I think I'll have to stop here. So I just wanted to spend a little time trying to finish up explaining how to compute the Hilbert space of a theory using geometric quantization. So we saw last time so for example, for U1 Chern-Simons theory on the two torus, the phase space is also the two torus. And the symplectic form is, say, something like k d theta 1 d theta 2. So we saw as well last time is when the symplectic form is d alpha, alpha is a 1 form, that the Hilbert space is polymorphic functions. And the phase space, well, where we have to choose a complex structure which is adapted to the symplectic form. So for example, in the case of just flat space, or 2, so if omega is dp by dq, then, well, P is, Z is P plus IQ, Z bar is P minus IQ, and so P is a half Z plus Z bar, Q is 1 over 2I, Z minus Z bar. So up to some factors of P and Q, so P and Q can become operators on by the rule that Z bar becomes d by dz. P gets sent to a half Z plus d by dz. And Q is sent to a half Z minus d by dz. Well, there's a factor of I here. I think I've missed an overall factor of I. You can check that these satisfy canonical commutation relations. And if we take the ordinary, so I'm just trying to explain something we very briefly discussed last time. Why, for quantum mechanics, does studying holomorphic functions lead to something like the ordinary Hilbert space? Well, so what we've seen so far is there are operators in the space of holomorphic functions, which are P and Q. You might look for the state which is annihilated by Q, or a state which is annihilated by P. And you could, viewing P and Q as raising and lowering operators, we could say take the state annihilated by P and hit it with the Q's to get the Fock space. So the state annihilated by P is something like e to the minus z squared over 2. So in this way, things which look like this, e to the minus z squared over 2, times some polynomial in z, will be the usual polynomial functions of Q acted on by raising and lowering operators. So times Q to the n defines familiar Fock space. Okay, so the other thing we didn't discuss last time is what happens if we work more globally. If instead of working with the symplectic form, which is the alpha, where alpha is a 1 form, what if the symplectic form can't be written like that? You have a question? Yeah.
Sorry. Oh, why do you say that partial z is equivalent to z bar?
Because the symplectic form is dz bar. So it looks like dp dq in these coordinates. So when we do canonical quantization, these are z and z bar are canonically conjugate.
Yeah, but when acting on any function of holomorphic function of z, is equivalent? Because z bar multiplied holomorphic functions, and then it's not a holomorphic function.
That's right, but I'm just so I'm making a similar definition to what you would do when you say I have P and Q that satisfy canonical commutation relations. My Hilbert space is functions of Q. P acts by d by dq. So I'm just doing something analogous to that by declaring, well, my functions do not depend on z bar. They only depend on z. And z bar acts by d by dz. Because of the symplectic form, makes them canonically conjugate.
I see.
So the more global picture so let's do an example, which is an example that Aldo discussed. Suppose we have a situation where the phase space is S2, which I view as C union infinity, and that the symplectic form is, well, it's the natural volume form of the two-sphere, which in the complex coordinate C looks like this, dz bar over 1 plus absolute value of z squared, and we normalize it so that the integral is an integer. So the rule is the following. So I'm not sure I'm going to have. I'm not sure I'm going to be very good at justifying this rule, but this is how it works. we choose a U1 gauge field on X so that, which is our phase space, the curvature divided by 2 pi I is equal to the symplectic form. Then choose holomorphic coordinates Ci in various patches. So omega looks like dZ's wet dZ bars. And then, so what we're going to do, instead of looking for holomorphic functions, we're going to think there's a couple of ways to say it. So one way is to say, because the equation that something is holomorphic is a differential equation. I'm going to replace derivatives by covariant derivatives of this gauge field. This is a really natural thing to do because, U1, when I study U1 gauge fields, U1 acts on C, and if I have some quantum mechanics with this state in C, I should study covariant derivatives with respect to that A. In any case, so the last part is, so we study functions z bar which satisfy del z bar I plus a z bar I so which are not constant, are not independent of z bar. We replace this equation by its covariant constant version. So the collection of such expressions is the Hilbert space. Okay, any questions? So let's study this for the two-sphere. I feel like I didn't prepare this part of the talk in as much detail as I would have liked. But let's see how we can go. Wow. I'm going to use a trick just to make life a little easier so we don't get stuck into formulas. So it is not hard to show this construction well, essentially only depends essentially, I mean, this on the complex structure and on the cohomology class of omega. Because for U1 gauge fields, on S2, so S2 is no circles that can't be contracted. S2 is simply connected. So for U1 gauge fields, two gauge fields whose curvature for the same cohomology class, they're gauge equivalent. Okay, you know what? I realize maybe this sentence is not so relevant. But let's proceed anyway. So suppose that the integral over the two-sphere of omega is some number n. Okay? Well, what we're going to find is that the number of states is roughly n. So we saw early on that if we want to have a gauge field whose curvature has this integral, the fact that the curvature is quantized is related to the winding number, the intersection of two domains. So then, the gauge field, so it can be trivialized on the region, say, z less than 1. So it's gauge equivalent to the trivial gauge field. And the gauge transformation on the overlap is something that winds around n times, so we'll take it to be z to the n. Okay, so so you can say, if we choose a gauge field which is the trivial gauge field over here, the trivial gauge field over here, and the gauge transformation looks like z to the n, what do the functions which are holomorphic in this covariant constant sense look like? So a state is given by, say, psi1 by psi0, a holomorphic function on the region where z is less than 2. Psi1, same thing, on the region where z is bigger than 1. So in particular, psi1 is really a function of 1 over z, so u equals 1 over z, and it has no poles at u equals 0. Sorry, that's not psi 1, that's psi infinity. But they're going to be related on the overlap psi infinity is equal to because we have this gauge transformation of the overlap, these two guys are related in this way. So what does this mean? So let's expand psi 0 in series. So psi 0 looks like 1 a0 plus a1z plus a2z squared plus so on. But z to the minus n, psi 0 has no pole at z equals infinity. So this means well, because I'm hitting it by z to the minus n, the first couple of terms are fine. I only get a problem after the z to the n plus 1 term. So a n plus 1, a n plus 2, so on are 0. So that's psi 0 is a0 plus a1z plus an plus 1, sorry, an z to the n, and that the Hilbert space is of dimension n plus 1. So Aldo explained how this symplectic manifold is going to be related to the to Wilson lines for SU2. The reason being that SU2 acts on the 2-sphere and preserves all of the structure it needs to be. So therefore, SU2 acts on the Hilbert space, so it's some representation. And what we find, well, we have some representation of dimension n plus 1. Well, what representation could it be? It must be the representation of spin n plus 1 over 2. So to see this concretely, so let's work away from z equals infinity. Then we're just studying holomorphic functions. Then the Lie algebra SU2, the SL2C, acts on holomorphic functions by del z these vector fields. Well, there's a slight subtlety which I didn't really explain. Psi 0, because of the presence of this line bundle, psi 0 isn't really a function. It's a tensor which starts with dz to some power. Psi 0 is a tensor. Really looks like dz to the power of n over 2 minus n over 2. And then you can check, if you want to calculate it, that these vector fields give you this the spin n+1/2 representation of SU2. Okay, any questions? I can't think it was particularly clear, but yeah.
Sorry, I didn't understand why it is a tensor.
Yeah, so let me explain that. So the reason is we have to think a bit, to see why it's a tensor, we have to think a little bit more carefully about these line bundles. So I just said you can make the gauge field trivial on one patch and trivial on the other patch. But those gauge transformations don't preserve the SU2 symmetry. So we need to think a little harder to figure out how things transform under SU2. So to see why it's a tensor, what we need to do is we need to understand geometrically, what bundle on the two-sphere has the feature that its curvature looks like that. Well, there is a natural bundle. Two-sphere has constant Ricci curvature. I mean, in 2 dimensions, there's only one kind of curvature. So the Ricci curvature is proportional to the metric. And omega kind of is the Ricci curvature. So what that means is, if we view that the Levi-Civita connection is a connection for the group SO2. Because in general, the Levi-Civita connection is a connection on the tangent bundle, but we can view it as a gauge field for the group SON on a manifold of dimension n. So here it's a gauge field for the group SO2. We call it gauge, because I've been using the word gauge field. And SO2 is U1. So because S2 has constant Ricci curvature, the curvature of this guy is the volume form on S2. Up to a factor. It's constant with some factor, and that factor appears in which multiple of the volume form it is. And omega is also the volume form. Now, the size, we're in some representation of U1, which is some representation of SO2. So the size become fields of some spin corresponding to how they transform under SO2. Psi is a field on SO2 of some spin. So that is, it lives in some 1D rep of SO2. And then if you calculate the spin is something like minus k over 2 or something. So that's ultimately why it becomes a tensor. So the key, I know it is a bit involved, the key point is that the connection is the Lebedev connection. And originally, when I said I had some state in the Hilbert space, it was holomorphic in a way twisted by the gauge field. It lived in some representation of U1. So therefore, it lives in some representation of SO2. Therefore, it's a field of some spin. Okay, so it's not, it turns out, sometimes it's true that you can relate, if your symplectic manifold happens to have a nice metric with nice positive curvature properties, then you can relate the symplectic form to the geometry in this nice way, but it's not, that doesn't often happen. The two-sphere is kind of special in that way. Okay, any other questions? I feel I haven't done a very sure job. I haven't prepared. So I want to say a little bit more about Chern-Simons theory, and then I'll stop. So we mentioned earlier the example of Chern-Simons theory on the two torus for the group U1. So let's also do the two torus for the group SU2. So it turns out that the phase space is S2 omega, as we just discussed. So this, in other words, because of this example we just computed, we now also know how to compute the Hilbert space for Chern-Simons theory in the two torus for the group SU2. And the integral over S2 of omega is related to the Chern-Simons level. So let me just try and say this very briefly. So by definition, phase space is the collection of flat SU2 bundles on T2 mod gauge. So here's my two torus, and if we cut it up, it looks like a square with sides identified. So a flat bundle, meaning vanishing curvature, so it's determined by the matrix of parallel transport around the A cycles and the B cycles. So it's determined by parallel transport of my gauge field along the A cycle. That's an element of SU2. And parallel transport of my gauge field along the B cycle. It's also an element of SU2. So the A cycle is that one, the B cycle is that one. Now, clearly, suppose I were to do the B cycle and the A cycle, that should be the same as the A cycle and the B cycle, because it's a flat gauge field, so it doesn't matter if I change my path a little bit, the parallel transport doesn't change. So that means these matrices commute. And also, these matrices are taken up to gauge transformation. So which means conjugation in this case, because a gauge transformation sends this matrix so if you recall why that is, if I have the parallel transport from here to here, I'm identifying this point with this point. So if I do a gauge transformation at this point by some matrix gauge transformation everywhere, well, at this point it takes some value m, it sends the parallel transport to m, p, m inverse. So let's try to classify this data. Well, up to conjugation, any element of SU2, I can diagonalize it. So I can choose a gauge. Where P along the A cycle is equal to lambda inverse. Say lambda bar, where lambda bar lambda is equal to 1. And then, since the parallel transport along the B cycle commutes, with this, we have PAB is mu bar. It's so. I mean, I put the A cycle one in this form, and that fixes the gauge entirely, almost entirely. And then that forces the other one to be in this form as well. So it looks like the space is, again, two circles. So it looks like, again, it's a two torus. But we have the remaining gauge transformation. by this matrix, and that interchanges lambda and lambda bar. So I get this. Wow, maybe I didn't write down the right matrix. There is a remaining gauge transformation which interchanges lambda and lambda bar. So the result, the phase space, is U1 cross U1 modulo Z2 where the Z2 action says lambda to lambda bar and U to U bar. So this space turns out to be a sphere. So there are 4 fixed points to the Z2 action. These are the solutions because there's 4 solutions to the equations. So the 4 solutions being lambda is equal to 1, lambda is equal to -1, So I think it's like a fairly well-known point in topology that if you take a sphere with 4 points and a double branch cover of a sphere with 4 points, then the double branch cover is a torus, and that's what we're seeing here. I could try to draw a picture to indicate why this is actually a sphere. Okay, are there any questions?
Yeah, can you draw a picture to show us?
I will try, yes. So what I'll do instead is show that if you take a sphere, 2 branch cuts, and a double cover where you cross the branches as well as cross the branch cuts, then you get a torus. So that's kind of the backwards way of seeing it. So S2, Z unit infinity. Consider 2 branch cuts. And then imagine consider a double cover.
Sir, where are these 2 branch cuts? Where are them?
Well, they're just they're at any 4 points in C.
Okay.
It doesn't matter where they are because I'm only interested in the topology and not the geometry of the space. Consider double cover, where as we cross branch cuts, sheets are glued. Switched. Give me a second. So this there's a nice picture. I just have to bring it to mind. So let's draw one sheet away from the branches. I'll draw this one that way, this one that way. Sorry. So if I just imagine what happens away from the branches, and I'm including infinity, we get this kind of thing. Over here is infinity. I'm going to look at this guy, and this guy. And the other sheet looks the same. And over here, infinity. So each of these sheets hits the whole plane kind of outside of these regions. And then you have to think about what happens as I go into this region. I'm going to glue the two things together. But this region...
You are in the Zoom meeting now.
Okay. So this region in here...
You are in the Zoom meeting now.
Okay, so that's a sketch of why... why the two torus, or identify opposite points, becomes a two-sphere, and here the four fixed points become the four branch points. Because the branch points are points that are, they have only one thing in the two torus mapping to them. So they become, the four branch points live there and there and there and there. Okay. Okay, so now we know how to understand the Hilbert space version of Simon's theory for SU2 on a two torus. The tricky part is like figuring out what's the volume of this two-sphere. But once you know that, like in terms of the level, once you know the volume of the two-sphere in terms of the level, you know what the Hilbert space looks like. But of course, the volume of the two-sphere is half of the volume of the two torus, so that's actually not so bad. So we conclude the Hilbert space for SU2 in Simon's theory at level K seems to be is quantization of S2 omega, where integral of for S2 of omega goes like k over 2, I think. There's some details about this, getting these normalizations right, which is a little tricky. But if we pin down all those details, we'll know what the Hilbert space is. So I think the last thing I wanted to briefly discuss is take an example we mentioned before. For G equals U1 and the 2 torus, and Simon's theory on the 2 torus, the phase space is again the 2 torus. And the symplectic form looks like d theta 1, d theta 2. So what is the Hilbert space? So step 1 is we choose any complex structure on the 2 torus. So the nice thing about having phase spaces which are Riemann surfaces is that every form looks like dz, dz bar, because you can't have anything with dz squared or dz bar squared. So we can use any complex structure. So when we choose a complex structure, the 2 torus looks like this. That is, we choose some tau with this imaginary part that's positive, and we identify the 2 torus with plane where z is made equivalent to z plus 1 and z plus tau. And this is the fundamental domain for this equivalence relation, and the opposite sides are identified. But the complex structure tells us how to rotate by 90 degrees. Like what we're saying is the rotation by 90 degrees is like just is not the same as the angle at which the sides meet. So the Hilbert space is then some modified version of the space of holomorphic functions on the 2 torus, and that's the same as the space of elliptic functions. Space of doubly periodic holomorphic functions on C. Well, so at this point, the analysis can get a little bit involved because we would say, well, we want to choose a gauge field whose curvature looks like this, and we want to vary the equation that something is holomorphic. And it turns out that you can, there's a couple of equivalent ways of saying it. It's not hard to write down something which is neither holomorphic nor periodic. So like e to the z bar. So it's possible to trade being holomorphic for being periodic. So one version of the Hilbert space will give rise to a space of functions which are not quite periodic, but have some twisted periodicity. So one way of doing this get functions with a twisted periodicity. So the way I find it a little easier, that's the standard way. The first thing I find a little easier to look at functions which have poles instead. And these will all lead to the same Hilbert space, just different parameterizations. So if the integral over the 2 torus of omega is k, we can assume that our gauge field is trivial away from some chosen point, away from this point here, the origin, and near the origin. And then the same arguments we saw for the 2-sphere says, well, if I want to have this feature, the gluing data, the gauge transformation which glues them, must have a winding number k. So the gluing is glued by the function z to the k on the disk near our point. So if we do that, then the Hilbert space is functions on C, which are doubly periodic, and with a pole of order k at the lattice points. So this is just like the sphere. The sphere, we had one patch, they were regular, and the other patch, they were regular, and they were glued by z to the k. So that allowed a pole of order k to appear at one point. So here, everywhere over here, they're regular, and on this disk, they're regular, but the gluing data has a z to the k. So that means if I extend the function from the bulk over here, it's allowed to have a pole of order k at this point. And this single point, it becomes all the lattice points when I view it as coming from a quotient of the plane. Right, so what are these functions? So if k is at least 2, these are functions 1, virus p function, derivative of the virus p function, and so on. This is a pole of order 0, 2, 3, and so on. Okay, so now we've understood in terms of elliptic functions what the Hilbert space for Chern-Simons theory for U1 and the 2-sphere on two toruses. And there's a similar story for U1 on a genus G curve. It's more complicated because you're dealing with higher dimensional tori. And this is just the start of the very interesting story about boundary conditions for, like, chiral boundary conditions for Chern-Simons theory, which are obviously closely connected with these meromorphic functions. But unfortunately, I won't be able to do that because the class is stopping today.